So, what do you, the fuel in your car, and a diamond all have in common? It all comes down to one single, incredibly versatile element: carbon. So let's dive in and uncover the chemical secrets that make carbon the ultimate element of everything.
I mean, just think about it. It's in the food that fuels you, the clothes you're wearing, and even the DNA that makes you, well, you. Carbon compounds are literally the building blocks of our entire world. But for an element this important, you'd think it'd be everywhere, right? Well, this is where things get really interesting.
Despite being the foundation for millions and millions of compounds, carbon itself is actually pretty rare. It makes up just a tiny, tiny fraction of the Earth's crust and atmosphere. So that presents a fascinating puzzle. What is carbon's secret? How can one little element be responsible for the massive and complex chemistry of life, of industry, of everything? Let's find out.
Well, the answer lies in two unique properties. You can think of them as two chemical superpowers that make carbon unlike any other element on the periodic table.
To get this, we first need a quick look at how atoms bond. Most atoms, they either give away or they snatch electrons from other atoms to become stable. That's called an ionic bond. But carbon's in a tough spot. It has 4 electrons in its outer shell. Gaining or losing 4 electrons is just a huge amount of work. So carbon does something way smarter. It shares. It forms these really strong, really stable connections called covalent bonds. Carbon isn't a giver or a taker. It's a sharer. And this brings us to its first superpower, tetravalency. Tetra just means 4. It means a carbon atom can form 4 separate bonds at the same time. This makes it an amazing connector, almost like a perfect little building block with 4 different connection points. Now for the second superpower, and honestly, this one is the real game changer. It's called catenation. This is the unique ability of carbon to link up with other carbon atoms, forming these incredibly long and stable chains, branches, and even rings. No other element can do this anywhere near as well. And if you want to see the power of this in action, just look at diamond and graphite. Both are 100% pure carbon, but their properties couldn't be more different. In a diamond, each carbon atom is locked into this tight, rigid grid with 4 others, which creates the hardest substance known to man. But in graphite, the carbon atoms link up into these flat sheets that can slide right past each other. That's why it's soft and slippery enough to write with. Same element, totally different materials. It's all about the arrangement. So you combine these two superpowers, tetravalency and catenation, and carbon becomes the ultimate chemical Lego set. It's capable of building a seemingly infinite variety of structures. But not all of these carbon chains are the same. You have saturated compounds which have only single bonds. They're very stable and kind of unreactive. Think of them as being full. But then you have unsaturated compounds. These guys have double or even triple bonds between carbons, and those extra bonds are like little handles, making them much more reactive and ready to build even more complex molecules.
And things get even cooler when carbon starts rearranging its own structures. This is a phenomenon called structural isomerism. It basically means you can have the exact same chemical formula, the same set of Lego bricks, but you can arrange them in totally different ways.
Butane is the perfect example. Both of these molecules have the exact same formula, C4H10. But look at them. The one on the left is a simple straight chain. The one on the right is branched. Same parts, different shapes, and that means they have different properties. This isomerism is a huge reason why carbon can form so many millions of unique compounds. But a plain old carbon chain is just a skeleton. To give these molecules their unique personalities, their smells, their functions, what they actually do, we need to add some accessories. In chemistry, these are called functional groups. They're specific clusters of atoms that can latch onto a carbon chain and completely define how that molecule behaves. The carbon chain is the skeleton, but the functional group, that provides the personality.
It determines the function.
So let's check out a few of these star players. You attach an OH group and boom, you get an alcohol, which is used in solvents. You attach a COOH group and now you have a carboxylic acid. That's what makes vinegar sour. That CO group, that's a ketone, the key ingredient in nail polish remover. These little groups are everything.
Okay, time to put all this together. Using everything we've just learned, from carbon chains to functional groups, let's solve a mystery we all encounter every single day. How does soap actually work?
So meet the soap molecule. It is a masterpiece of carbon chemistry and it has a dual personality. It has this long hydrophobic tail that's just a carbon chain that hates water but loves oil and grease. And then it has a hydrophilic head, an ionic part that loves water.
So, when you wash your hands, the soap molecules swarm any oily dirt. Their hydrophobic tails dive right into the oil, grabbing onto it. And at the same time, all the hydrophobic heads face outwards, staying in contact with the water. This incredible little structure is called a micelle, and it's a perfect trap for dirt.
The final result is just ingenious. The oil and dirt are now trapped inside this molecular cage, completely surrounded by the water. So when you rinse, the water-loving heads allow the entire micelle, dirt and all, to just get washed away. It's an absolutely elegant solution, and it's all thanks to the unique properties of carbon.
So, to answer our big question from the beginning, carbon's incredible versatility isn't magic. It's a direct result of its ability to share electrons in 4 directions. That's tetravalency. And its unmatched power to link with itself. That's catenation.
And before we go, let's just quickly bust a few common carbon myths. First off, when a chemist says organic, they are not talking about your groceries. They just mean pretty much any compound that's based on carbon. Second, while we think of carbon compounds as coming from nature, chemists have actually been making them in labs since 1828. And finally, soaps and detergents are not the same thing. Detergents are specifically designed to work in hard water, which has minerals that make regular soap form that gross scum.
So, if you remember just one thing, let it be this. The simple, powerful, and incredibly stable bond between carbon atoms is the ultimate reason we have such a rich and complex world of chemistry all around us.
Which of course leaves us with a huge question. Carbon's unique properties make it the foundation for all life that we know of. But could a different element, maybe its cousin, silicon, play the same role on another world? What kind of life would that create? Now that is something to think about.